Okay, so let's just quickly recall what we had done in the previous lecture. We had concluded the fact that if you have a linear operator, that suppose T is a linear operator over a finite dimensional vector space V, such that the characteristic polynomial for T factors completely, factors completely over the scalar field, obviously, over the scalar field. Then we have some ordered basis, then there exists an ordered basis for ordered basis of V, such that the matrix of T with respect to this ordered basis is in Jordan form, right? Is in Jordan form. Okay. Okay. How had we defined the Jordan form, if you quickly recall? So an elementary Jordan matrix and elementary Jordan matrix, this was defined as a matrix of this form, right? So we have scalars throughout the diagonal and then we have one below each scalar, right? And zero everywhere, right? So this was our elementary Jordan matrix. And how we had decomposed the linear operator into matrix form is that if we have something of this form, then if I let A to be this matrix, then A is a direct sum of matrices A1, A2 till some AK, let's say, where each AI is a direct sum of Jordan blocks, right? We had said this to be J1I, J2I till JKI, let's say JNII, right? We have done this, and so each JJI is an elementary Jordan matrix, right? Or we say this is Jordan matrix of characteristic value C, of characteristic value C. So if the characteristic polynomial considers distinct scalars, say Ck, each of these are obviously your eigenvalues for the linear operator. So each JJI is a elementary Jordan matrix with characteristic value Ci. Clear? So that was what we discussed in the previous lecture. And so let me just state a few facts regarding this. For example, that if two matrices are in Jordan form, and they are similar, then they can differ only in that the order of the scalars are different. Okay, got it. So let's just quickly discuss the fact. So what we do is that, let me just write the goal of it. We want to show that if two matrices are in Jordan form, that if two matrices are in Jordan form and and are similar, then they can differ only in the order of the scalars. Okay, they can differ only in the order of the scalars Ci. Okay, so how do we kind of claim this? Suppose I choose an ordered basis B of B. Let B be an ordered basis of V such that A, which is the matrix of T with respect to B, it's in Jordan form. So it's a Jordan matrix. Right? It's a Jordan matrix. So we just go back to the direct sum decomposition of this matrix A into Jordan form, which we did in the previous lecture. So if you recall, A is a direct sum of some AIs, where each AI was a DI cross DI matrix. If you recall, so the matrix AI is a DI cross DI matrix, where if you observe carefully the way we formed this Jordan form, that where DI is clearly the algebraic multiplicity of these eigenvalue Ci. Okay, that is, we had actually denoted the characteristic polynomial to be x minus c1 to the power t1 and so on to x minus ck to the power tk. This was our form, right? So I guess it's obvious, right? Now, obviously, since this forms a characteristic polynomial, so each of these scalars c1 till ck and each of these exponents d1 till dk, they are unique, right? Therefore, the scalars c1, c2 till ck and the exponents d1 till dk are unique up to the order in which we write them, right? In which we write them. Clear? Now A is a direct sum of these AIs, right? A is a direct sum of these AIs. So if A is a direct sum of these AIs, then we can write V as W1 direct sum till WK, where each WI is T invariant, right? The matrices AIs are kind of the matrix representation of each of these WIs with respect to the induced operator TI. If you just recall, or if we come from the other way around, that if since A is direct sum of AIs, we come from here. A is direct sum of these AIs, then we can write this like this, and WI is the null space of T minus CII. Okay, right? N is surely the dimension of V. Now, why does this happen? For AI minus CII is nilpotent, right? It's nilpotent from the definition of AI. AI is simply Jordan, it contains just the Jordan blocks along its diagonal, Jordan blocks corresponding to the eigenvalue Ci, right? So it's obvious that AI minus Cii is a nilpotent matrix, and if I choose the index j, where j is not equal to I, then this is non-singular, right? Its determinant is non-zero. It's non-singular, right? Therefore, each Wi is unique. Therefore, each Wi is unique, and if we induce the linear operator Ti by T, then obviously, as I said, that AI was the matrix representation of each of these Ti. Right? So if Wi is unique, so this Ti should be unique. So AI is should be uniquely determined. So AI is uniquely determined by the rational form, of Ti minus Cii. Okay, so that's what we are talking about. Now, how can we calculate the Jordan form of a given matrix? Let us quickly go into that, and we will discuss a few examples related to Jordan form. So, calculating the Jordan form. What we do is that now, suppose A is in Jordan form, we are kind of relating the structure of A, which we discussed in the previous lecture. That A is a direct sum of matrices A1, A2 till AK, where each AI is containing the Jordan blocks of the characteristic value Ci, and it's of dimension Ni cross AI, Ni cross Ni. Where we are going through that basis. Okay. Okay. So yeah, we will obviously be coming up with the significance of each of these indexes as well. Let me just go through it. Now every entry of AI, every entry of A, it's not immediately zero below the main diagonal, right? So every entry of A not on or immediately below the main diagonal, below the main diagonal is zero. Okay, that's quite obvious because we are concerned about a block form. We are not giving a diagonal form. We are giving a block form, right? So we are giving a form like this. So like this, right? Right. The blocks appear along the diagonal, and it seems like to be along the diagonal. Suppose if you have here 2 0 1 2, here you have 3 0 1 3. So the matrix is typically of this form, right? So it's 2 2 3 3 3 3. We have 1 here and we have 1 here. So obviously, immediately below the main diagonal, the elements are non-zero. At least, in fact, over the main diagonal, the elements are also non-zero. So we are talking about this only. Clear? Okay. On the diagonal of A, what happens? That's what we are concerned about. On the diagonal of A. So this was clear from this block form, right? So on the diagonal of A. See, in the Jordan form, we have the characteristic values along the diagonal. So in each matrix AI, we have the characteristic value along the diagonal. So therefore, in each in each matrix A, so in the matrix A, the diagonal comprises of the characteristic values only, right? So on the diagonal of A occur the k distinct characteristic values, k distinct characteristic values C1, C2 till Ck of t, right? And also from the characteristic polynomial, it's obvious that the algebraic multiplicity of each Ci is di. Therefore, each distinct characteristic value Ci will appear di times, right? Also, each char value Ci appears di times. Appears di times. Okay, where the characteristic polynomial is x minus Ci to the power di. Product like this, I is equals to 1 to k, right? So precisely di is the algebraic multiplicity of Ci. That's what we wanted to talk about. Okay. Number two is that for each I, the matrix AI is a direct sum of Ni elementary Jordan matrices, right? This was clear from the structure. For each I, AI was a direct sum of Ni number of Jordan matrices. Of Ni number of Jordan matrices, which we represented as JJI, and each JJI corresponded to characteristic value Ci, which uh, corresponds to the characteristic value Ci. Okay. How can we determine AI? So precisely Ni is the dimension of the eigenspace. Right? It's the dimension of the eigenspace of Ci. Other way around, these Ni's sum up to uh, I equal to 1 to k. They sum up to the dimension of V. Okay. Clear? Okay. Now, if I go back to the way we extracted out this Jordan form, then we get that Ni is the number of elementary nilpotent blocks in the rational form of Ti minus Ci, right? So I will always refer to go back to the previous lecture to completely thoroughly understand the previous lecture and then come to this lecture. Otherwise, some terms will be misunderstood. Okay. Now, in the previous lecture, we had that Ni is the number of nilpotent elementary nilpotent blocks. These are the elementary nilpotent blocks in the rational form. In the rational form for Ti minus Cii, and that's exactly equal to the null space of T minus Cii, right? Okay. What we can say about diagonalization from here? What happens if Ni equals to Ti? So Ni corresponds to the dimension of the eigenspace of Ci. If Ni then equals Di, then that would mean the dimension of the eigenspace exactly equals the algebraic multiplicity. If you quickly recall the terminology we used in case of diagonalization, the null space of the eigenspace, we had considered that to be the geometric multiplicity of the characteristic value. So if Ni equals to Di, that instead means the geometric multiplicity of Ci is exactly equal to the algebraic multiplicity of Ci. So therefore T is diagonalizable. T is diagonalizable if and only if Ni equals to Di, right? Okay. Number 3 is that now how can we calculate the Jordan blocks? That's also quite easy. For each I, the first block Ji, the block J1I in AI, so it's a Ri cross Ri matrix, right? It's an Ri cross Ri matrix where Ri is the multiplicity. This is very important. Is the multiplicity of the characteristic value Ci as root of the minimal polynomial, as root of the minimal polynomial for T, right? And how does this follow? This immediately follows from the fact that since Ti minus Cii, this is a nilpotent operator, and the index of this nilpotent operator is Ri. So typically the minimal polynomial comes out to be, so I shouldn't say the index to be Ri. The minimum, so this is a nilpotent operator, and we had previously seen that the minimal polynomial of Ti minus Cii comes out to be x to the power Ri, right? So it directly comes from here. Okay. So what we typically need to do is that if we are given the characteristic polynomial and we are given the minimal polynomial as well, just check the just check the multiplicity of each of the characteristic values with respect to the minimal polynomial, form Jordan blocks using that very dimension of the as the exponent of that, as the multiplicity of that characteristic value as a root of the minimal polynomial, and just place each of these blocks along the diagonal, and you will get your Jordan form. One thing which is very precise from here is that if the underlying field is algebraically closed, if the scalar field is algebraically closed, then the polynomial, the characteristic polynomial will obviously completely split. If the characteristic polynomial completely splits, the minimal polynomial will completely split, and hence we can always get a Jordan form, right? So if F is an algebraically closed field, if F is an algebraically closed field, then every matrix over F, has a Jordan form. Okay, every matrix over S has a Jordan form. Clear? And we also get a straight matrix result that if we have a if you have an n cross n matrix over a algebraically closed field F, we are working with an algebraically closed field F, such that it's similar to a n cross n Jordan form, n cross n Jordan matrix. Then the matrix Jordan matrix is unique up to rearrangement of the order of its characteristic values. Okay. So if I just phrase this, I want to say is that if B is a n cross n matrix, over a field F such that B is similar to A, where A is a n cross n Jordan matrix, then A is unique up to rearrangement. This we saw in the previous observation, up to rearrangement of the characteristic values, right? Of the characteristic values. And when B is similar to a Jordan matrix, we say this matrix, this Jordan matrix, to be the Jordan form of B. Okay. A is said to be the Jordan form for B, or Jordan form. Okay. Let us quickly go through a few examples and then we will end this lecture. Okay. The next lecture will be more important because in the next lecture we will come up with a matrix manipulation of matrices over, sorry, I should say a row manipulation, row and column manipulation of matrices over polynomial rings over the field of over the polynomials over a field, uh, and we will kind of define the elementary row and elementary column operation as we used to do in the scalar matrices, because we will, using that, we will come up with an algorithm to find out the invariant factors of a given matrix. So if you quickly recall what invariant factors were, they were the T annihilators of the vectors alpha 1 till alpha r, which gave us the cyclic decomposition of a given finite dimensional vector space. Okay. So question number 1, or I should say example 1. I'll frame it as a question. Show that any 2 cross 2 complex matrix, is similar to either a matrix of the form C1 0 0 C2 or C1 0 1 C2. Okay. Proof. Okay. Now see, we are given a an algebraically closed field, right? So the characteristic polynomial will obviously split. So let A be a 2 cross 2 matrix over C. Let me just define it like this. So A is a 2 cross 2 matrix over C. Let F be the characteristic polynomial. We will abide by the notations we have already used. Let F be the characteristic polynomial of A and P be the minimal polynomial of A. P be the minimal polynomial of A. Obviously, F will split because we are under a algebraically closed field. So we can write, let F be of this form, x minus C1 times x minus C2. Okay. C1 can be equal to C2, C1 can be different from C2. What happens if C1 is different from C2? Suppose C1 is not equal to C2. Then it's obvious that this matrix has distinct eigenvalues, right? All the eigenvalues are distinct. Only two of them are there, so both the eigenvalues are distinct. So it's diagonalizable, right? Therefore, A is diagonalizable. And that's also because of the fact, because in this case the minimal polynomial will also be the same thing. So therefore A is diagonalizable, and then A will surely admit this form, right? And A will be similar to this form, C1 0 0 C2, right? What happens if C1 equals to C2? Now let C1 be equal to C2. Let us assume that to be the value C. Then the characteristic polynomial comes out to be of this form, right? X minus C whole squared. And what are the possibilities for the minimal polynomial then? Then either it can be x minus C, or the minimal polynomial can be equal to the characteristic polynomial. If the minimal polynomial is x minus C, then again it's diagonalizable, right? Because we have seen that a polynomial is a matrix is diagonalizable if the minimal polynomial splits into linear factors, right? So if P is x minus C, then A is diagonalizable. Right? Then A is diagonalizable and A admits the form. Then A is similar to C C 0 0. So it's again the first form, kind of the first form. right? What happens if P is x minus c whole square? Here we need to consider the Jordan form. How do we consider the Jordan form? So it's quite similar, because what is the multiplicity of the eigenvalue c with respect to the minimal polynomial? It's 2, right? So if you relate back to what we had done in the steps we had given to calculate Jordan form, here Ri is 2, R1 you can say, R1 is 2. So if R1 is 2, then the J11 matrix, it will come out to be 2, 1, 2 and 0. And that should be exactly equal to AI, and that should be exactly equal to A, right? Sorry, not 2, C, right? C, yeah, C, right? And that's exactly the second form, right? That's exactly the second, right? That was quite trivial. Let us consider one more example. Example 2, let's say, consider a complex matrix. Consider a complex matrix is given as A being 2, 0, 0, A 2, 0, and B C minus 1. What can we say about the matrices which A can be similar to? I guess that is also called the similarity classes of A. It consists of those matrices which are similar to A. So yeah, let's check it. What is the characteristic polynomial of A? This is a lower triangular matrix. We can just multiply the diagonal elements. The diagonal elements will give you the eigenvalues. So the characteristic polynomial of A is precisely x minus 2 whole squared times x plus 1. Right? What are the possibilities for the minimal polynomial then? The minimal polynomial can either split into linear factors of this form, uh, or it can be exactly equal to the characteristic polynomial. These are the only possible cases, right? If this happens, then A is diagonalizable. Then A is diagonalizable. So if A is diagonalizable, then A is similar to the matrix 2, 0, 0, 0, 2, 0, 0, 0, minus 1. Before moving on to what the Jordan form will be, let us first discuss a very interesting notion, that if the minimal polynomial is of this form, right, then the minimal polynomial will obviously annihilate A. Then look, the value of A minus 2i times A plus I, this should be equal to 0. Let us calculate this matrix first. What is A minus 2i? A minus 2i is 0, 0, 0, A 0, 0, B, C, and here you have A minus 2, so it becomes minus 3, and here you have so here you have A plus I, right? So you have 3, 0, 0, A 3, 0, B, C 0, right? What does this give you? So if you just carefully calculate it, what should this give you? So you have 0 times 3, 0 times A, 0 times B. So first element is 0. Okay, all the elements in the first row will be 0 because the first row is 0 on the first multiple. Then you have A times 3. Then you have 0 times A and 0 times B, correct? You have A times 0, 0 times 3, 0 times C, 0, A times 0, 0 times 0, 0 times 0. So this element is 0 again, right? And this row will also be 0, right? Lastly, what you have 3 times B plus AC, right? So 3 times B plus AC minus 3 times B, so it's 0. It's AC, right? 3B plus AC minus 3B, so it's AC. And the other elements, what should you have here? You have B times 0, 3C minus 3C, 0. That is exactly 0, right? But this should be exactly equal to the 0 matrix. And what is the only possibility for it to be 0 matrix? A needs to be 0, right? Which should imply A is 0. Therefore, we have concluded the fact that A is diagonalizable. In this case, A is diagonalizable if and only if A is 0, right? Right, it's obvious. What can we say about the Jordan form? So we have the characteristic polynomial as x minus 2 squared, x minus 1, x plus 1, and we have the minimal polynomial exactly equal to the characteristic polynomial like this. So how does the Jordan block for 2 will form? Okay, the Jordan block for the characteristic polynomial 2. Let me name let me name it like this. So this block will be of dimension which is equal to the multiplicity of 2 as a root of the minimal polynomial. So it should be a 2 cross 2 matrix, right? So we have 2, 2, 1 and 0, right? The Jordan block for the eigenvalue 1 will be a 1 cross 1 matrix. It consists only of the element minus 1. So the Jordan matrix should be of this form, right? So it should be of the block form J2, J1. These elements are 0. So this is precisely the block 2, 0, 1, 2 and the element 1. All the rest of the elements are 0. So this should be the Jordan form. Minus 1, right? Yeah. Okay. Is it clear? Okay. The next example is also very important. It will kind of show us the fact that even if the characteristic and minimal polynomial of two matrices are same, they need not be similar. Okay. Example 3. We choose the matrix A to be 2, 0, 0, 0, 1, 2, 0, 0, 0, 0, 2, 0, and 0, 0, A 2. The first thing to observe from here is that observe that A is a direct sum of two 2 cross 2 matrices. If I consider this to be A1, if I consider this to be A2, then A is clearly a direct sum of two 2 cross 2 matrices, A1 and A2. Right? Right. What is the conclusion which we can bring out directly from here? That is, if A equals to 1, then the matrix is already in Jordan form. What is the characteristic polynomial of it? It's x minus 2 to the power 4. Right? We have A as a direct sum of two matrices. Right? Then what should be the minimal polynomial of it? The polynomial for each of these matrices should be x minus 2 whole square. So the minimal polynomial comes out to be x minus 2 whole square. Right? Right. Now if A is equals to 0 or if A is equals to 1, then A is indeed in Jordan form. Okay. If A is equals to 0 or A is equals to 1, then A is in Jordan form. A is in Jordan form. Clearly the multiplicity of 2 as a root of the minimal polynomial is 2. So the Jordan block will be of dimension 2 cross 2, right? Therefore the matrix we would be eventually getting for the Jordan form must be A, right? But we have respective values of A to be 0 or 1. In either case, what are the matrices we get? We get 2, 0, 0, 0. We get 1, 2, 0, 0. We have 0, 0, 2, 0. And we have 0, 0, 0, 2. And the other matrix we have is that 2, 0, 0, 0, 1, 2, 0, 0, 0, 0, 2, 0 and 0, 0, 1, 2. Are they similar? Recall the fact we had said that the two Jordan forms are similar only if they differ in the order in which the characteristic values appear. These two have no difference in the order in which the characteristic values appear. Instead, they have difference in an element itself. They cannot be similar by uniqueness of the Jordan form, right? Still having the same characteristic polynomial and the same minimal polynomial. Right? So we had previously seen this, that if two matrices are similar, then they have the same minimal and the same characteristic polynomial, but the converse need not be true. That if two matrices have the same characteristic and minimal polynomial, they need not be similar. Okay, clear? So let this lecture be up to this much. In the next lecture, we will be starting with computing invariant factors of a matrix. Okay. So meet you guys in the next lecture.